Hi, Jack and Kim. I had to go sub for a study hall, so I'm trying to catch up, getting ready in here. And it's freezing in here because I opened the windows. All right, ladies and gentlemen, welcome back to in-person class time.
No, probably. I think
I'll go ask them.
Do you see a trash can on either side of my desk? Thank you.
No, I don't.
Hey, you got a speaker thing.
I know, isn't it like fancy? That's the intercom.
Oh.
You know how they would just walk down the hallway whenever they needed me for something?
Oh,
Now they can yell at me through the intercom.
that's a little startling. It's just coming from behind you.
Woo!
Yeah.
Well, like the first day I worked here, I think like people were in the building and I was in the cafeteria with like the science department. And Mr. Sobolewski came on the intercom and just said something like, "Let us pray." And I just went, "God?" Because apparently I have issues. God? Yeah, it really is. Well, my husband is really terrible with dad jokes at this point. Like, he's fully embraced the dad joke thing.
Oh, yeah.
I think you're right.
Yeah.
But I can't.
Sorry, I'm doing attendance.
Maybe she'll follow me. Maybe her account will follow me.
Oh my gosh. Oh my gosh.
I didn't allow that.
That would be amazing.
Before the end of high school.
Yeah.
I'm just like, like, even though I already know the number, you wouldn't be like, like, I'm signed into it.
All right, you guys ready to get started? All right, ladies and gentlemen, boys and girls, welcome to in-person class. Yay! So, I do want to make sure that we recap the lab activity that you guys did. But we're not going to start there. We're going to start with talking about worksheet number 1. Because I think that if you understand worksheet number 1, some of the things we did in the lab activity will make more sense. Does that sound okay? I'll tell you what else. First period was kind of like, they said, we have more questions about this, and we didn't ask them last week. So I'm just going to tell you guys about worksheet number 1. Cool? All right, so you guys are going to want to follow along. All right, so we're going to talk about worksheet number 1 today. Good news is that I did this during first period, so hopefully this is smoother than it was for first period. Just stay over there, people. You guys okay back there? Corey, don't bully other people. How many times do I have to tell you guys? All right. So, you guys should have your worksheet number 1 from Unit 3 handy. Guys, Unit 3. You ready? All right. So, on the first page, the thing that we need to do, hold on, we go back. So in this worksheet, what we're going to be doing is looking at the same data. So this data table is the data that we use through the entire thing. The data doesn't change. What changes is the way that we're analyzing it and the way that we're representing it in different types of graphs. So we're at a point in physics class where we can use several different kinds of graphs to be able to describe motion. In the beginning of the unit, we just started with tables, a position versus time graph, a motion map, written expression. And now we can actually get to the point where we can analyze the data a little bit, which gives us different graphs we can use and allows us to derive different equations. And so that's what we're going to do with this worksheet. So when you're drawing a graph like this, it's really handy, especially if you're just hand drawing, to make it as big as possible, because then if you're drawing a line and you need to figure out slopes or something, you have a lot more options. So I already kind of figured out how this should go. So earlier I'd set mine up so that along the bottom, every 5 blocks was 1 second. So to do that, 1, 2, hold on, I have to count. I can't count at the same time. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, so maybe you guys did that the same. Maybe you did it a little bit differently. Sometimes students. Oh, I'm so sorry. Why isn't it up there? I know. It's just I'm at the point where I like connect so many things anymore. I'm just like.
Let him be funny. Let him be funny.
We better? I can make it brighter. Okay. So across the bottom, I used 5 columns for every second. My hope is that you guys did 5, like 4 or 5. I hope that you guys didn't just make one block 1 second, because then you have a very, very tiny graph, and it's very difficult to do anything with it. So this works a little bit better. We want to make sure that we label these, so I'm going to label this time and seconds. Do you guys have questions? Okay. And then along the side, I made each row worth 5 centimeters. So that means we start with 0 down at the bottom. 1, 2, 3, 4. 1, 2, 3, 4. Just gotta eyeball these better. So, I hope you guys are noticing that I don't label every single one. I just skip them and label them. 60, 180, 200. All right, so there we go. So now I've got all my grids labeled. I'm ready to fill in my data. So using my data table, I've got a dot at 0, 0. I've got one at 1 second and 5 centimeters. Position. You guys are doing a good job labeling your graphs, right? Position, time. 2 seconds and 20 centimeters. 3 seconds, 45 centimeters. 4 seconds and 80 centimeters, 5 seconds and 125, and then 6 seconds and 180. There we go. So did you guys get some dots that look like that? Yeah, it's not a straight line, is it?
No.
Because in our last unit, we always got a straight line. We did position versus time. Now we've got a curvy line. Oh no. What did the slope of our line in the last unit mean? What was the slope? Yes. So I heard speed up here, but also velocity. So the significance of slope on a position versus time graph, velocity. Speed is velocity without direction, right? So if we do position and time, we draw a line there, then that's going to give us our velocity. So on our new graph, what happens to our slope? Remember slopometers? You take your slopometer, right? Like I can measure the slope between 2 points. So there's my slope between those points. If I move towards 0, does my slope get smaller or bigger?
Smaller.
Smaller. If I move it this way, what does it do? It's bigger. So as time goes on this graph, our slope is increasing, right? If it's increasing, what does that tell us about our velocity?
It's increasing.
It's increasing, and what do we call velocity that changes?
Acceleration.
Yeah, that's acceleration, right? You know, like in your car when you push the gas, right? Do we call that the accelerator? So we hit the gas, right? We hit the gas, our car goes faster, and we say that it's accelerating. So when we see a change in velocity, this is telling us that the speed or the velocity is increasing. And what does that mean? If it's increasing? Yeah. Can you accelerate in a negative way?
Yes.
Oh, is decelerating a thing?
No.
Yes.
No. Decelerating is
Charlie, yeah.
Accelerating is not real.
Decelerating.
Ah,
Flash is what it is.
okay, so if we So sometimes, guys, sometimes when you hit the brakes or you're going up a hill and not applying enough gas, your car slows down, right? Your velocity decreases. So that would be, in physics class, considered to be a negative acceleration. But I know that everybody calls that deceleration, right? Yeah, so we at least know what we're all talking about. That's all the same stuff. All right, so the next thing that we're asked to do, because we've got all these, you guys remember these groups of things to do? Groups of things. So, y'all with me? When you start chatting, I'm worried that you're not listening to me anymore. Not because I'm vain, just because I want to make sure everybody gets all the information. Okay, so the first one says, on the position versus time graph, draw a line that connects the points at t equals 0 to the point at t equals 6. So what I'm going to do is connect this guy down here with this one up here. And I know that you guys are all, what's the correct word here? You're students who know how to solve problems. And so if you need a straight edge that goes between those dots, like use a piece of paper or folder or something. And you can kind of go between those two lines. And I'm going to draw a line that connects them. So if I was only worried about the initial and final position of my object, I could have a line that looks like that. Yeah. So if my line is red, I'm not sure if you guys can see the color very well. So it says calculate the slope of this line in the space below. And so what I'm going to do is I'm going to record my time and position for those 2 points. So my times are 0.0 and 6.0. The position is 0.0 for 0 seconds and 180 centimeters for 6 seconds. So guys, if we are looking at those positions, right, we said that this was going to give us an average velocity across those points. And so we've got a position at 6 seconds and a position at 0 seconds divided by time at 6 seconds divided by time at 0 seconds, right? This is just final minus initial. You guys have seen this before. This should be familiar. So those position is 180 centimeters minus 0 centimeters divided by 6 seconds minus 0 seconds gives us 180 centimeters for 6 seconds, which is what? 30 centimeters per second. Yeah, okay. So that tells us our average velocity over that time period is 30 centimeters per second. Is that the velocity here? Is it the same as the velocity here?
No.
This is the average, right? Okay. The next one. On the position versus time graph, draw a line that connects the points at 2 seconds. I don't want to use purple. At 2 seconds to 4 seconds. So now I'm going to go back to my graph. Here's 2 and 4. I'm going to be resourceful. Grab my piece of paper / straight edge, and I'm going to connect those 2 points. There they are. What do you notice about the slope of that line and that line?
Parallel.
What? Okay, so if that's parallel, what do we expect the value to be? The same. So if my time is 2 seconds, my position is 20 seconds. And if my time is 4 seconds, centimeters, then my position is 80. those of you who are quick with math can already look at this and say 2 seconds, 60 centimeters. What do we got?
30 centimeters per second.
Mm-hmm. You guys sound like that's not exciting at all, and it's
Oh,
so
that's what
exciting.
Charlotte- I love it.
Look at that. It's the same, guys. Okay, so if that blue line represents an average velocity of 30 centimeters per second, is that the same as the velocity here? Same as here? Or here? So where along this line would it be equal to 30 centimeters per second? Thoughts?
At 3.
Why do you think at 3?
Because it's in the middle.
I mean, like, that's a reasonable thing to test, at least, right? So look at this. Number 9. On the position versus time graph, graph a line tangent to the graph at 3 seconds. This is the one that got you?
I don't know how to, like, we never learned how to draw a tangent line.
It's just like.
Oh, my bad.
That's okay, we're gonna do it again. Okay.
Oh.
Oh, you guys. I have solutions for these things. I just don't like cables. Where's my wireless computer power? Come on. Okay, so tangent lines. What you want to do with the tangent line is draw a line that never crosses our purple curve. Right? Both the red line and the blue line would cross the purple curve. Right? And we're asked to do a tangent line at 3 seconds. So we have to draw a line that goes through that point that doesn't cross either the purple curve on either side. Right? You with me yet, Sam?
Yeah, so you just draw.
If I drew a line here on this edge, it would cross the purple curve. If I drew a line like this, it would cross the purple curve. So I've got to figure out how to draw it so it doesn't cross the purple curve. Here's the thing, like, I hand drew all this. So, like, we have to do the best that we can here.
How, did you just draw the same slope as the 30?
As the 30. Well, do you think it is?
Yes.
I mean, if I start with that blue line like that and I kind of just scooch it over until it intersects that point,
That's 30.
you like it?
Yeah.
Okay. So what I'm going to do, I'm going to grab a marker I haven't used yet. Oh, come on. This one always does that. Okay, so I'm going to go through. How'd I do? Okay. It's parallel. Does it cross purple line?
No.
Not really.
It kind of does. We know.
Sam is horrified by my line drawing.
No, not you. No, I'm saying I don't think it is.
No,
30.
it wasn't you.
I don't think it's 30 at 3.
So I'm just trying to pick 2 points on this line because I need points, right? If I'm going to calculate this, you could, if you wanted to, use the point at 3. I'm just picking ones in other places. So thanks, Clarence. Okay, so the ghost is Clarence. We did. Okay, so at 2.2 seconds, I have a point that's at 20 meters. And then I've got a point at 4 seconds that is 75 meters. Okay, so there we go. There's my data from those 2 points that I chose on the line that I drew. What's the risk if I'm using data from a line that I drew? It could be off a little bit. Okay, as long as we recognize that there is the potential for error here. All right, so our change in position is going to be 75 minus 20 meters. Our change in time is going to be 4 seconds minus 2.2 seconds. So we got 55 meters for 1.8 seconds. How did we do? Math? Yeah. So 55 divided by 1.8. I got 30.6. Is that close? Is it good? Actually, that's better than I did first period. All right. What does that mean, guys? What does it mean?
Wait.
We need success. So, all right, let's take a look at this. Wait,
Was it centimeters or meters on the left?
centimeters. Most of the time we use meters per second. That's why I kind of got thrown off. It should be centimeters. I do appreciate you keeping track of my units for me,
have on
though.
the left and then on the.
Yeah. All right, guys. So if we can use these 2 data points, these 2 data points, and these 2 data points, and basically get the same slope, what does that tell us about what things we can do with our data? There's a magic thing here. It's not necessarily about linearizing, but the thing to notice about it is if you have a single point of data, like any of these points, how do you figure out what the velocity is at that time? Yeah, but like my tangent line is the worst calculation, right? If they should all be the same. If they should all be the same, guys, check this out. If I want to know the what's called the instantaneous velocity at 3 seconds, I can say, you know what? That only gives me 1 data point. If I want to know the data point there, that's going to be the same as the average velocity for the 2 data points that are an equal amount of time on either side. Right? The equal amount of time is the important part there. So if I want to know the velocity at 3, I need to measure the velocity between 2 and 4.
Gotcha.
Or I could use 1 and 5, or I could use 0 and 6. If I want to know the velocity at 5, I can find that by using the position and time data for 4 and 6, because those are both an equal amount of time away from 5.
Wait, since we already know the average, like that, the red line, what is that orange?
Yeah,
So is that's the same slope the entire way, right?
yeah, it's the same slope all the way.
So every point's instantaneous velocity would be 30?
No, just the middle.
Just the midpoint. So if you have the average velocity from 0 to 6 seconds, and there's one caveat here, guys, and it's constantly accelerating, so it's constant acceleration, then that average velocity from 0 to 6 is the same as the instantaneous velocity that's exactly in the middle of that time.
So it would be is 3
At 3. Yeah.
3 in the middle.
Yeah, 3 is the middle.
So like if it was from 1 to 3, the instantaneous velocity at 2 would be the same.
Yes. Yeah. Because you'd be doing, this. And up here it would be, if you did these 2, it would be the same as that. Yeah. So tangents are the very messy way to do it. It'll work, but you have more space there for errors. If you need to know the instantaneous velocity of a single point, the best bet is to go an equal amount of time in either direction, as long as you know that it's uniform acceleration. So yeah. So then on number 12 on your worksheet 1, it says consider an object accelerates uniformly. If you were to calculate the average speed of an object for a given interval of time, would the object ever be traveling with the instantaneous speed equal to that average speed? If so, when? Yes. At exactly the midpoint in time in the travel of the object. You guys have any questions about the first part? So that's our first way that we can represent an object that has constant acceleration. We can use a data table and a graph of position versus time. Excuse me. So now, second part. You okay? This next one? Just hold it up, let me look at it. It might be okay. It's the right shape. Okay, so guys, now we've got a data table here. You'll notice if you take a look at this is the same values as you have on the first problem. We're going to do a slightly different analysis, though. I know, it's like magic physics. Don't use these party tricks to impress your friends at parties. Like, you'll be like me and have a lot fewer friends.
Oh.
I have really good friends. I just don't have a lot of them.
Just a small unfortunate.
Okay, so we need to, the instructions here tell us to fill in the table. So the table over here is the table on the right that we're going to fill out. The first row, the first column is the change in time for each of these measurements. So if we look at this, the way the time is changing, it increases by 1 at each point. So these are going to each increase by 1. Easy peasy. The next one is change in position. So I'm going to look at how the position changes as we move down the data. So here, 0 to 5 is a difference of 5. 5 to 20 is a difference of 15. 20 to 45 is a difference of 25. I see patterns. Ooh.
Yeah.
Yeah, I can.
It kind of looks like.
Patterns have predictive power and lets you forecast the future, guys. Like, come on. All right, 45 and 55. Oops, 55.0. All right, next it says T mid. So this is another thing we have to calculate. This is the midpoint in time between each of these data points. So in between here, it's going to be 0.5. Next one, 1.5. Next one, 2.5. Next one, 3.5, 4.5, 5.5. And the last thing we have to calculate here is the average velocity. This is going to be our change in time, our change in position divided by our change in time. So we're going to take this column divided by this column. I got 5.0, 15.0. Because all the times are 1, it's just change in position, just with different units. Okay, did we do okay on the table, guys? All right, now what we're going to do is take these 2 columns of our table and make it into our graph. There we go. That's what we're going to graph. Let's see. Dr. O'Malley doesn't like the way Dr. O'Malley set up this table down here. So Dr. O'Malley is going to just edit this a little bit. There we go. All right, so this is going to be time. Our instructions tell us that this is going to be a velocity versus time graph. So we've got time along the bottom, and we've got velocity on the side. You guys have questions? No? Okay. So time's on the bottom. I'm going to divide this up so that every 4 blocks is a second. So there's 0, 1, 2, 3, 4, 5, 6. I'm trying to be careful with these because if you label the squares wrong, sometimes your graph looks funny when you're done. I've seen really extreme cases where kids will like be doing this and all of a sudden they'll put like the next one there and then it'll dogleg and it's not a line. Well, yeah, it's not a line. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 4. All right, and I'm going to label these guys 10, 20, 30, 40, 50. So guys, there weren't any instructions on how you should lay this out on here, except I do encourage you to spread it out as much as you can. So if you chose a different interval here, that's okay. Right? You're not going to be wrong because you chose the different interval. And now I have to figure out how to put my data points on the graph. Now, the biggest mistake that I see students make with this particular one is with figuring out where to put your data point on the timeline, because see how this says midpoint time is 0.5? A lot of students say, oh, my first point should be at 5 centimeters per second, and they scooch over here to 1 and then figure out what the velocity is. You actually need it to be at the halfway mark. So it's going to be at 0.5 and 5. So my first point should actually be there. My next one is going to be a 1.5 and 15. 2.5 and 25. And again, being careful about your graphs is going to make it easier to get the right answer when you do your analysis. 3.5 and 35. 4.5 and 45. Oops, I almost put it in the wrong place. 5.5 and 50. Mine looks like a line. Did you guys get a line? Cool.
Yes.
Lines are a good thing because in physics class that means we can make an equation for this.
Yippee.
I know, right? How many of you guys are in calculus?
I don't think anybody's in calculus.
Nobody in here is in calculus?
Worksheet.
I think all my calculus people sorted in the first period, which is interesting. So when you take calculus, guys, you'll start to see this kind of thing. You'll see in calculus, how to take something that is a curve and make it into a straight line. Anyway, so we've got a velocity versus time graph for our data, and now we can make an equation for it. And so to make an equation for our graph, we know that this should be in the slope-intercept form, right? Y equals mx plus b. Do we have an intercept here?
0.
It's 0. I'll tell you what, I'm just gonna be like, this is 0, I'm not gonna worry about it today. So y is our velocity in centimeters per second equal to, now we need to figure out our slope. So I like to do slopes by using the first and the last data point if I can. Like this is a straight line, so we don't have to worry about average slope, it's just the slope. So our slope is going to be our change in position, our change in velocity, or our change in time, right? And so this is going to be 55 centimeters per second minus 5 centimeters per second divided by 5.5 seconds minus 0.5 seconds. Right? What are we going to end up here with, guys?
10.
It's 10, Dr. O'Malley. Can't you see it? What are our units? Okay, if we've got centimeters per second divided by seconds,
No, it's just centimeters.
then it's going to be centimeters per second times 1 over seconds.
Oh, it's centimeters per second, right?
It's going to give us centimeters per second squared. Have you guys ever seen units like this before? Where we've got a distance divided by time squared. All right, what did we say earlier when we were talking about the slope of our curvy line? That if our line curves, we have a change of velocity as time is changing. What do we call that change in velocity? Acceleration. What are our units for acceleration? Like when you see a commercial about a car, how do they describe how fast something can accelerate?
0 to 60.
Yeah. So they say it goes 0 to 60 miles per hour, and what? And they tell you how long it takes, right? So that's what this is. This is a velocity as it's changing. Okay? So guys, our number that we're going to put here is 10 centimeters per second squared, right? And this is going to be times time squared seconds. No, this is just time. I got ahead of myself. I want to erase it, and I lost my eraser thing. Look at that, I made it look gross. I'm going to fix it. What did Mr. C. Fang do? There we go. All right, you guys see this one? Okay, what is this value, this 10 centimeters per second squared? It is, but what does it represent? Acceleration. So this right here is acceleration, guys. Do you guys notice when we look at this graph? This is telling us that we can tell what the velocity is as time goes on. So we can see that our vehicle is getting faster and faster as time goes on. You guys see that there? I feel like you're making fun of me.
No, I actually do.
Okay, so here's another thing. Velocity is equal to acceleration times time, okay? That one's important. We're going to come back to that one. So draw a circle around it or something. You do. You should write it down.
11.
Velocity is acceleration times time. Guys, check that out down here. If we rearrange this a little bit, and we make it acceleration equals velocity We have to divide both sides by time, right? Isn't that the same as this right here?
Oh.
Hey, yo.
I really can't tell if you guys are making fun of me.
No, this is mind-boggling.
I have no idea.
So I'm not going to teach you guys like 50 equations. I'm going to teach you like 3 or 4.
Yeah.
So that you guys don't have to memorize a whole bunch of stuff. Okay.
Nice circle.
Anybody have questions about number 13? How much time do we have left? Ooh. Okay, guys, we're going to do this one. No, it's going to be great. I don't know why these words are over there, but there they are. They just ran off. All right. So, guys. On this page, we are going to take that same data. You guys see it? It's the same data. Same data. Now we're going to linearize it. Did we linearize it over here? Kind of. We manipulated it and graphed something completely different. Now we're gonna linearize it like we would have if we were looking at this data in the first unit. Do you guys remember we got that whole chart of how to linearize different shapes of graphs? Do you guys remember that, or is it too far in the past? All right. So we're gonna linearize it by squaring time. Did this happen, by the way, in the Pivot Interactive activity that you did?
Yes.
It did. Okay. So now I'm going to go through and I'm going to do these in my head because I can. She said because math. Okay. So hopefully you guys didn't struggle too much with that one. Again, Dr. O'Malley doesn't like Dr. O'Malley's graph at the bottom, so I'm going to change it. Modification. There we go. And we need to put times on here. So I'm going to do, how many did I do? I'm just going to make these like 5. 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. Okay, so there's, oh, wait a second. I put the wrong numbers down there. No one stopped me. So guys, now my time goes from 0 to 36. So instead of having 6 seconds across here, I need to make these much bigger. 10, 15. I have seen students, so check and make sure that you didn't do this. Like put it on these kind of guys or not spread these out. I've seen that happen before. 1, 2, 3, 4. So my biggest one is 36, but I'm just going to mark 35 there. So these are all time squared, which means my units are seconds squared. All right, and then on the side here, I need position in meters. So I need some more.
Centimeters.
Yeah, I just did like every 4 was 20.
Yeah, me too.
Wow, really,
Awesome.
Sam?
Yeah, that's crazy.
That is actually kind of.
That's crazy. Isn't it? That's what I'm saying. It's like.
I actually don't think it's that weird. Okay, so far so good. And then we got to put our data points on there. So for 0 seconds, I'm at 0 meters. So I'm right here at the bottom. Then next, I'm at 1 second and 5 meters. So I'm very close to the bottom. You can see how close those two are down there.
That's
And then 4 and 20. I know when you start to linearize things, it makes your graphs look funny. 9 and 45. I think that's right. 16 and 80. That's too far. 25 and 125. 130. Okay, so okay. 36 and 180. So we're here. I think it's there.
Yeah.
Nope, it's one over. There it is. Okay, did I get a straight line?
Yeah.
Woo! Okay, so guys, what's the slope of that line?
1. No. Then four.
We're doing our change in position, right, divided by change in time, t squared. All right, so our initial position is 180. Our final position, our initial position was 0 and our final was 180. And then this is measured in centimeters. For time, our final is 36, and our initial is 0, and that's seconds squared. What did we say it was? Somebody math it?
It's 5.
5 what?
Centimeters per second squared.
Okay. So when we do our mathematical analysis here, we've got our y equals mx. Do we have a b? 0. 0. Okay, so our y is position, right? Oops. Sometimes when I do a parentheses, I mistake it in my brain as a c. That's what I'm doing.
I do
You do that a lot?
that. Yeah.
Yeah, like doing the two curves really messes with me. Equals 5 centimeters per second squared times time squared seconds squared. Okay, guys, what can we make of this? What's that 5? What does it mean?
Velocity.
So on this side, our slope was 10, and it has the unit centimeters per second squared, right? Over here, we've got 5 centimeters per second squared. What's the relationship between those two things? What do you have to do to get to 5 if you start with 10?
Divide by 2.
Divide by 2. Okay, so how about this? I'll just make it simpler. You guys ever seen that before?
Probably.
So that's going to be another one of our significant relationships, is that we can figure out what the position would be if we know the acceleration and the time. It's snazzy. Snazzy. All right, I think we've got a minute and a half left, guys. Before tomorrow.
What is the slope equal in that one?
What
does it represent?
Represent.
It's 1/2 times the acceleration.
Oh, so it's not like it's not like the velocity or anything, it's just half of the acceleration.
Yeah. This is velocity equals acceleration times time. So there's things you could do over here. Like you can make it because a times t is velocity. So if you wanted to start messing with that equation, you could do 1/2. You can mess with it.
Oh, yeah.
But you wouldn't want to, but you could.
So if you have an addition in time, then it comes out as exponential.
But you guys,
Eat together, it's in a spread out fashion. Don't forget, folks, after you eat today, make sure you wash your hands, keep your masks up.
you can watch them now if you want.
Family room representatives, as we have pictures and other mails for everyone. Thank you.
Okay, what were you saying?
So if you were to linearize the graph by squaring the time, then you would get half of the acceleration.
Yeah. I'll show you guys how to do this digitally too, though. So you're not going to have to do this very much. I just want you to understand where the equation comes from. Because we just took the same data table and produced 3 different graphs and 3 different equations, right? Because if I told you guys hey, draw position versus time, and give me the equation for this, you guys would be like, nope, not going to do that. It's a little absurd. Hey, Kim and Jack, do you guys have any questions for me? Cool. So guys, everybody, just make sure you have that last page done for tomorrow, and we'll check that part in for a grade, okay? Have a super day.